The last part we are looking at is cleavage patterns of common functional groups. So the first pattern is alpha cleavage. That means the alpha position of the amines, carbonyls, and alcohols will be cleaved. The second cleavage is McLafferty rearrangement. This only happens to carbonyls. If you have a carbonyl here, see this carbon? So that's a carbonyl carbon. If the fourth carbon, so starting with the carbonyl, 1, 2, 3, and 4. If the fourth carbon has a hydrogen, then that will go through McLafferty rearrangement. The other way to look at it is, instead of saying the fourth carbon, we can say the gamma carbon. So the alpha carbon is the carbon immediately after the functional group. See, the functional group, the carbonyl carbon is that. So that's the first position. And then the first carbon after that becomes alpha. And then the next carbon after that becomes beta position. And then the carbon after that becomes gamma position. And then the next one after that becomes omega. So if the alpha carbon or the fourth carbon, has a hydrogen, then that will go through McLafferty rearrangement. And then the last kind of cleavage is dehydration. This only happens in alcohols where you lose water, and water is H2O. The mass of that is 2 for hydrogen plus 16 for oxygen, which gives you an M/Z value of 18. So anytime you see a loss of 18, that will show that that's an alcohol, and that's because you're losing water. And that's basically a dehydration, almost similar to elimination reaction. So for example, if you have an alcohol like that, OH, and then you lose water, you're going to lose a hydrogen from that position and OH from there, so that you end up losing water. And that basically will be the first hydrogen plus the OH, so that's the water. Then you end up with an alkene at that position. And that's because you're losing water, so minus 18, M/Z value of 18, which corresponds to loss of water because it's an alcohol. Now let's look at the other two rearrangements in detail. Alpha cleavage. Now if you look at these three examples, number 1 is alcohol, number 2 is amine, and number 3 is a carbonyl functional group, which could be an aldehyde, as in this case it's an aldehyde. It could be a ketone, an ester, or carboxylic acid. The carbon that's connected to the functional group is the functional group carbon. So same thing with the amine, that's the functional group carbon. And same thing with the carbonyl, that carbon is a functional group carbon. Now, the next carbon after the functional group carbon becomes alpha position. So same thing with amine, alpha position. Same thing with the carbonyl, alpha position. The next carbon after that is the beta position. Beta, beta. Then the next one after that is gamma position. So in alpha cleavage, you end up cleaving the alpha position. So you break that carbon. So between the alpha and the functional group carbon, which will give So after you cleave the alpha position, you end up splitting the molecule into two. On the right hand side, you have that carbon and the OH. So that's that carbon there, CH2 and the OH. Same thing with the amine, you have the CH2 and the NH2. Same thing with the carbonyl, you have that carbon. But on the left side, the side with the alpha carbon, you break that and now it has a positive charge. It's a charged fragment. And that's why we have M/Z ratio, which is mass to charge ratio. The fragment has to have charge for the instrument to be able to detect it. Please review my other presentation on how mass spectrometer works. And then you can calculate the mass of these fragments. So that will be CH3 group, so that's 15, CH2 group 14, And this other one is also CH2 group 14 because it was connected to something else. So you end up with 43. So the M over Z value of this fragment will be 43. Now remember, if this is the structure, you will end up seeing a peak for 15, a peak for 15 plus 14, so 29. You'll see 15, 29, and 43. So that shows that you have a CH3 connected to a CH2 connected to a CH2. We're done with that. Now let's focus on McLafferty rearrangement. For McLafferty rearrangement, we're going to look at the carbon positions. So remember, we have alpha, beta, and gamma. If the gamma carbon has hydrogen, in this case this is a CH2 group, so we have 2 hydrogens, we're going to only show 1, then that can go through a McLafferty rearrangement. What happens in a McLafferty rearrangement is that that hydrogen ends up connecting to that oxygen, so you end up forming a bond between hydrogen and oxygen, and then the bond between carbon and hydrogen, the electrons flow back to make a double bond, and then at the same time you break the beta alpha carbon, those electrons go to between alpha and the carbonyl carbon to make a double bond. And therefore the product is, now you have a hydrogen connected to that oxygen, and then between alpha and beta you end up with a double bond. You break the beta alpha carbon, and then between the alpha carbon and the functional group, the carbonyl carbon, you end up with another double bond. You end up with this product, and that's McLafferty rearrangement. Looking at this example, that's the carbonyl carbon, the functional group carbon, and then the next carbon will be the alpha carbon, alpha position, and then the next carbon will be beta position. The next one is gamma. You actually have 2 gamma positions, but this gamma is very far away from the carbonyl, so you ignore that. You only focus on the other gamma. That gamma has 2 hydrogens. So remember, the requirement is that we need to have at least 1 hydrogen on the gamma carbon. In this case, you end up with a McLafferty rearrangement, where again the hydrogen will connect to the oxygen, the electrons will flow to make a double bond at that position, and then the beta alpha carbon will break, and those electrons will flow to between alpha carbonyl carbon position to form a double bond. First, this oxygen connects to the hydrogen. Then at the same time, the carbon hydrogen electrons going to form a double bond. So you end up with a double bond at that position. And then you end up breaking this bond. So you end up with a double bond at that position, and you break that bond. And then at the same time, you already used the other electrons for the double bond carbon. That will be the McLafferty rearrangement product.